Okay, so hello everyone, welcome to the problem solving sessions for Introduction to Automata Languages and Computation, week 12. So, this week we will look into another model which is called Turing machines. Okay, and we saw context-free languages. We saw that PDAs essentially recognize the context-free languages, and we saw some closure properties last time that context-free languages are closed under union, clean closure, and so on. So what we will see is how to show that a language is not context-free. So last in the previous weeks we saw what is called a regular language, and we know that DFS recognize regular language. We know if you want to show that, so this is the set of regular languages. So we know that if you want to show that some language is inside this set, then it's sufficient to give a DFA, NFA, or any of the equivalent models for it. But if you want to show that a language is not regular, that is it is outside here, uh, then you use what is called as a pumping lemma for regular language. So you have pumping lemma for regular languages. Now we saw that this context-free languages contain the class of regular languages. So if you want to show that a language is regular, then what we do is you give a PDA for it, or you give a grammar, a context-free grammar for it. But how do you show that something is outside? We know that there are things that lie outside. So how do we show that? For that you have what is called a pumping lemma for context-free languages. So how do we show that something is not context-free? Using pumping lemma. So this pumping lemma is very similar in spirit to the DFAs. In principle, it's very similar, but just that there are a few more things that we need to take into account while using this pumping lemma for context-free languages. So today we will look into some examples of that kind. We will see how to show that a particular language is not context-free. So let's see how to do that. Okay, so let's see the first question. Suppose that L is a context-free language and let's say R is a regular language. Now the question is, what can we say about L minus R? Is this necessarily context-free? So just to connect things, suppose L1 and L2 are two context-free languages, then what can we say about L1 minus L2? Is this necessarily context free? So yeah, so note that this is not the case, because L1 minus L2 is same as L1 intersection L2 L1 intersection L2 complement, and we know that L2 itself need not be context free, and even if L2 were L2 complement, sorry, if L2 is context free, it does not imply that L2 complement is context free, because we know that CFGs are not closed under complementation. So CFLs are not closed under complementation, and at the same time you have that even if let's say L1 L2 complement were context free, we know that L1 L2 is CFL does not imply that L1 intersection L2 is CFL. again for the same reason that it is not closed under intersection. Okay, so for these two reasons we know that L1 and L2 are context free does not imply that L1 minus L2 is context free. So if L1 L2 are, or we can just simply say that CFLs, therefore CFLs are not closed under the set minus operation. Okay, so yeah, so this is what we know. Okay, so now given this, now the question is saying that okay, let us relax the condition. Suppose L2 is not a context free language, suppose we know that it is a regular language. So in addition we know that, let's say L is CFL but R is regular, and now you want to show that L minus R is regular. So this is the question. So yeah, so if you're watching the video, then I would suggest that you think about it for a while, maybe pause or something, and then look at the answer. Okay, so we will show that L minus R is regular. So how do we do that? So let's say L is context free, then there must exist some M which is a PDA. There must exist a PDA M such that L of M is equal to L. Okay, so this must be the case. Then what do we do is, we want to make sure that one thing we know is that if R is regular, then there is a DFA, let's say N, such that L of N is equal to R. So this is also something we know. Now notice that what we want to do is we can write L minus R as again L intersection R complement, and we know that regular languages are closed under complementation. So this is same as L intersection R. So it suffices to show that if you have a context free language and a regular language, it suffices to show that L intersection R is context free. Okay, so this is what we know. Now okay, I'll get a new page here. So okay, so now what we do is we know that if let's say M is the PDA, then there is some machine which has some stack associated with it and some set of states that goes like this, and finally at the end when the stack is empty, it reaches the final state. So that is something we know. Now what we want to do is, we have this regular language R. What we want to do is, we want to somehow parallelly simulate a string X on the PDA, and at the same time we want to simulate it on the DFA. Okay, but one advantage that we have now, which we did not have when R was any context free language, is that we don't need a stack for R, because DFAs do not have a stack associated with it. They simply look at a state, look at the symbol, and then make their transition depending on that. So we don't really need a new stack in order to take care of this R. So what we'll do is, we'll simply make changes to these states so that it will also accommodate for the regular language. So let's say that this M was something like, you have a set of states, you have a stack alphabet, you have an input alphabet, you have accepting state, maybe I'll call it T, then you have a start state and a transition function. So this is what you have. And for the regular language n, you have, let's say, q prime, you have q0 prime, you have an accept state, you have a set of accept state, you have symbols, and you have a transition function delta. Okay, so what we will do now is, let's say this is the start state of uh, the PDA. Then according to the transition function, it is going to make some transition. Okay, so let's say it sees some alphabet 0, then, and let's say the top of the stack is Z, then it's maybe going to make some change like this and goes to Q1. So what we will do is, we will construct a new machine where the set of states um, is a tuple of p comma q, such that p is a state in q and q is a state in n, in q prime. Okay, so yeah, so what you have is, if you have q0 here and q0 prime here, then this is going to be a new state, and you're going to make all possible states like this. So these are going to be the new states of the machine. And what is the transition? So transition on uh, p comma q, on reading an element, let's say a, is that you go to a state delta p of a and delta prime q a. Okay, so basically, if you want to simulate, it's something like a cross product construction. This is basically the cross product construction that we are doing. So the set of states is all possible multiplications of this, and uh, yeah, and this is going to do the same action as as your earlier machine M was doing. So if it says that you should pop something, then you do the same thing. If it says you should push something, then you should push the same thing. The only thing is, if it were going to some state here, it will also have another part of the tuple here which corresponds to the DFA. And when should you accept? You should accept when your new state of final state would be when you are in the accept state of the PDA, as well as the accept state of the DFA, because we are doing intersection here. So just like in cross product, we only accept when both of the machines land in the accept state. So we're going to do the same here. So you will end up accepting only if Q is in F. So that is the only thing. So it's just that at the same time as you are doing operations on the stack and moving on the PDA, you are also making one step of the DFA. You're moving forward towards it. So yeah, so that is the whole construction. So this thing that we have designed is a new PDA. Design a new PDA for L intersection R. So that is the language, and therefore you know that L minus R is context free. So this is the solution for the part A. And now the second part says, what can you say about R minus L? Is it true that R minus L is necessarily context free? So the part B says, is R minus L context free? Okay, so let's see how to show this. So suppose that so the answer is no. We will show that this is not necessarily context free. So let's say R is nothing but sigma star, and L is the language, L, A to the n, B to the n. mm, okay, so L is the language, which is L1 union L2, where L1 is set of all um, A to the I, B to the j, C to the k, such that I is equal to j, and L2 is the set of all A to the I, B to the j, C to the k, such that j is equal to k. Okay, so this is L1, this is L2, and we know that L is context free. This is simply because we know that for this we can simply write a context free grammar. For L2 as well, similarly we can write a context free grammar. In fact, we've done this exercise earlier. So we know that, again we know that the context free languages are closed under union. So if L1 and L2 are context free, then L has to be context free. So this is what we know. So what we will do is R minus L is nothing but sigma star um, intersection L complement, and this is nothing but set of all A to the I, B to the j, C to the k, such that I is equal to j and j is equal to k. So this is nothing but A to the n, B to the n, C to the n, where n is at least 0. So we know that this language is not context free. So by pumping lemma, which we have done in the class, so we will not prove this for prove that this language is not a context free grammar using pumping lemma, because we did this in the class, but we will see some other examples. So by pumping lemma, we know that R minus L is not context free. Okay, so so that was the second part. So part A says that L minus R is necessarily context free. Part B says that R minus L is not necessarily context free. And now part C says that suppose you have a language which consists of strings which have equal number of A's, B's and C's, then is that language context free? So let's write this language formally. So I'll get a new page. So let's look at the language we are seeing. So A is the set of all W, such that if this denotes the number of A's in W, then number of A's in W is same as number of B's in W, and this is same as number of C's in W. So the question is A a context free language? So yeah, so hint is try to use the part A that we showed. So part A was that if if L is a context free language and R is a regular language, then the part A asks to show that L minus R is context free. Yeah, so maybe I'll wait for a minute so that you can think about it. Okay, so let's see how to show this. So we will show that answer is no, this is not context free. So suppose Okay, assume towards contradiction that A is context free. Okay, so suppose A is context free, then what do we know? That um, then we know that L intersection R is context free for any regular language R. So this is something that we know. So in particular, choose R to be A star, B star, C star. So that is any number of A's followed by any number of B's followed by any number of C's. So this is a regular expression, and therefore we know that this is regular. We know that this is regular. So what does, and choose A to L to be A. Then what does A intersection R look like? This is A star, B star, C star intersection A, and A basically says that number of A's is equal to number of B's is equal to number of C. So this is nothing but A to the n, B to the n, C to the n, where n is greater than equal to 0. So that means that this language, this implies A prime is context free, but this is a contradiction, because we know that A to the n, B to the n, C to the n, this is not context free. So that means our assumption is not correct. Hence A will have to be A is not context free. So this is where we use the part A. And then we basically made an appropriate choice of the regular language R, such that we get a language which we already know, which is already established uh, to be not context free, and this is how we showed that the language that is given to us is not a context free language. So notice that we've done something very similar earlier in the context of regular languages. Here, instead of A to the n, B to the n, C to the n, you had just number of A's is equal to number of B's, and using the exact same ideas, we showed that the language is not context. Okay, so if that is clear, then I'll move on to the next question. So yeah, so the next question is that you have been given a context free grammar, and in particular this is a context free grammar for regular language. So what the question asks you to do is, you want to design a finite automaton, that is a DFA, for this grammar. So it is guaranteed that this grammar is a grammar for regular language. So hence it is indeed possible to give a finite automaton. So yeah, I'll maybe wait for a few minutes. Hi. Okay, so let's look at the solution. So one thing that is very peculiar about this grammar, one observation is that every production is of the form that you have a terminal that first gives you a set of some terminals here, and only then it has a non-terminal, and it has a single non-terminal. So then you have a non-terminal. So it is in this specific form. So such grammars, these are called right linear grammars. This is because every non-terminal will always be on the right hand side. So let's look at this. In case of the first production here, the non-terminal is already pushed to the right, and before that you only have terminal. Similarly, if we look at this, then the non-terminal B is already pushed to the right. Then you can always ask the question, uh, can we have analogously left linear grammar? So indeed there is something called left linear grammar. So what is left linear grammar? You will have productions of the form S gives A followed by some string here. So you will always have non-terminal to the right, to the left. So hence these are called left linear grammar, and as an exercise you can try to show that every right linear grammar can be converted into left linear and vice versa. So this is something that can be shown, but that is not the point of this exercise. What we're going to do is, now that we know that the grammar that is given to us is in this form which is right linear, we will use this to build our DFA. So let's look at this. So the grammar says that S gives A or B. So what we do is, we think of S as a start state, and what this we interpret this as follows. So S, if you are at a state S and if you see uh, an element A, then you are going to reach to a state A. So these are the states, and if you see a letter A, then you should go to capital A state. And similarly, if you are at S and you see a letter small b, then you should go to the state capital B. So this is what it represents. So this is the partial state diagram that we are getting from the first production rule. Okay, so let's look at the second production rule. So this says that A gives this says that A gives B or epsilon. So what we will do is, we will write the rules for this. So what this says is, from A, if you read B, okay, let me do it step by step. So suppose you are at A and you read B, then you should go to capital B. This is how it is written, but we know that in case of DFS it is not possible. So if you are at Q0, then we don't write transitions of the form that A gives goes to B Q1. If we want to if we really want to simulate this, what we do is, we break this into states. So maybe this is a new state that I'm adding, and you break the transitions into pieces so that Q0 is still going to Q1 on reading AA, but you have an intermediate state. So that is exactly what we will do. So we will break this into two small pieces. So let's say C is some dummy state here. So you have C where A goes to B first and C goes to B on B. So we have still simulated that capital A goes to capital B on reading BB. This is from this transition, but we have broken it into pieces so that we are consistent with the definition. So now we have already captured this part. A gives epsilon is something we have not done yet, but we will do it later. So let's look at the third transition. This is capital B gives small a capital A or small b capital B. So what we will do is, if you are at capital B state, which is here, and if you see if you read small a, then you should go to capital A. So that is what we will write. On seeing small a, you should go to capital A, and if you see small b, then you should stay at B. So this is the diagram where we have four states right now, S, A, B, C, and we have captured all the transitions except for this one, which is A gives epsilon. So now what this means in terms of context free grammars is that, if you try to expand this, let's say S gives A and A gives, let's say, B capital B, and so on, the only way for this grammar to generate something is when finally all the non-terminals will terminate into some terminal thing. In this case, that is only possible through A. So only A gives epsilon is something that goes to terminal. Everything else takes you to some new non-terminal. So that's why what that means is, if you reach the state A, then you should accept, because then only you generate the string. So that means A is your accept state. So in place of A, in place of this, let's say that B also give epsilon, then B also would have been a final state. So there would have been two final states, but in this case there is only one symbol, that one transition that takes us to epsilon, so hence only A is the final state. So okay, so this is the final DFA that we get. So maybe I will highlight this. So this is the DFA for given grammar. Okay, so yeah, so one thing that is that can be seen as an extension of this exercise is that if you have a right linear grammar, you can always convert it into a DFA, and similarly if you have a DFA, you can always convert it into a right linear grammar. So these are equivalent things, and that's what we demonstrated with the help of this example. So yeah, I hope this is clear. If there are any questions, please do ask. Okay, so I'll move on to the next question. So okay, so this is an exercise for pumping lemma. Let's recall what is a pumping lemma for context free languages. Okay, so it says that it is very similar to what we have for regular languages, but it's just that it has some extra things to take care of. So we say that if L is a context free language, then yeah, then no matter what string you take, if X is in L, then X can be broken into parts. Maybe X is not a good notation, so maybe let's say a string P is in L, then it can be broken such that you can write this as UVW. Okay, yeah, you can write this as UVWXY, where length of PWX is at most n, and length of Vx is at least n, and you can pump it as many times as you want. So you can pump this as many times as you want, and the resulting string will always be in the language. So just to contrast this with the regular languages, what we had there was, for every string in the language you can break it into UVW, such that length of UVW is at most n, and length of V is at least 1, and U V to the I W is in the language for all I greater than equal to 0. So it's very similar to what we had for the regular languages, only that you have some extra condition over V and X is here. That is because your that is because how your PDA works. So yeah, so it comes from there. But even if this looks very abstract at the moment, when we look at the examples, I hope things will be clear. So let's look at the first example. So you have this language 0 to the n, 1 to the n, 0 to the n, 1 to the n, and we want to show that. So if I call this L1, to show L1 is not context free. Okay, so maybe I'll wait for a minute. If you would like to try using the pumping lemma, then we will discuss in a minute. Okay, so let's discuss. Okay, so yeah, so suppose that n is the pumping length for us. Then we look at the string x, which is look at the string 0 to the n, 1 to the n, 0 to the n, 1 to the n. And what we're going to do is we are going to break this into parts. So this is u, v, w, x, y. We're going to break it such that length of v, w, x is at most n and length of vx is at least 1. So we are going to look at all possible partitions of this string which satisfy these two constraints. So let's see how is that possible. So suppose that vxy, so there is a string of zeros, there's a string of, then there's a string of ones, then there's a string of zeros, and there's a string of ones. So suppose that this length and chunk of vwx, it lies here. Suppose it lies entirely within a block of ones, or it lies entirely within a block of zeros. So there are only few possibilities. Either vwx lies here, that is it covers all the ones, or it lies entirely here, or it lies entirely here. And the other cases are symmetric, when instead of here the ones lies here, or instead of here the ones lies here. These are symmetric cases. Or the only other possibility is that it is interspersed. So maybe it takes some zeros from here and some ones from here. So maybe the vwx chunk looks like this. But it can never be the case that the chunk looks like starts from here and goes till here. This is never possible, because in order for that to happen, it will have to cross over all the n ones here, but the length of this chunk is n only, so it cannot ever happen that you started at this 0 and you went at this. So there are only three cases, not even three, basically there are, in general there are only two cases possible. So we will show that for this there is a contradiction, and for this also there is a contradiction. The other cases are very similar, and you can assume without loss of generality. So let's look at the first one. Suppose that we write u as, case 1 is u is a chunk of zeros, v is vwx is a set of n ones, and the rest part is xy is 0 to the n, 1 to the n, doesn't matter. So then by pumping lemma, what this says is every u, v to the I, w, x to the I, y should be in the language for all I greater than equal to 0. So now now suppose I is equal to 1, then what this would say is u, v u, v square w x square y, this is nothing but 0 to the n, 1 to the n plus 2, 0 to the n, 1 to the n. So this says that this should be in the language by pumping, because by pumping it w, v and x one more time, what we have is you have increased the number of ones by 2. So that means that this string should also be in the language, but this is a contradiction, because the only strings that are in the language are of the form n number of zeros followed by same number of ones and so on. So this is a contradiction, this is a clear contradiction. So case 1 is not possible. Now if we do the same thing for case 2, suppose v is some zero, some set of some number of zeros, w is w is k1 minus some zeros followed by some zeros, and x is some number of ones. Then what this means is that either we are going to increase the number of v's or number of zeros by, again you choose I to be 2, then either you're going to increase the number of zeros by pumping extra v's, or you're going to increase the number of ones by pumping extra ones. So a string of the form 0 to the n plus 1, 1 to the n, followed by 0 to the n, 1 to the n, this is again not in the language. So because pumping this would increase the number of zeros here, which does not match the number of zeros here. Similarly, if you pump ones here, then there would be more ones than the number of trailing ones here. So again you get a contradiction. So yeah, so that's the whole point, that in either of the cases you show that such a pumping is not possible. So the next example is very similar. So instead of same number of zeros and ones, you have a separator. So part B is, let's say L2 is the language, 0 to the n separated by 2n many ones, separated by, sorry, yeah, separated by 3n many ones, and we want to show that this is not context tree. So again we want to use the pumping lemma, and idea is very similar, that we want to look at all possible chunks, all possible breakings, and show that in each case there is some contradiction. So I'll maybe wait for, yeah, sorry, yeah, so I'll maybe wait for a minute if you would like to try. Okay, so let's look at the, okay, so let's look at the solution again. Let's say that the string that we are looking at is 0 to the n separated by 2n many zeros, separated by 3n many zeros. Now we are again going to break this as u, v, w, x, y, such that the two conditions are satisfied, such that first the length of v, w, x is at most n, and second is that the length of vx is at least 1. So these are the two conditions that we still want to satisfy. So notice that it is never possible that vwx, or um, yeah, or let's say it is never possible that v or x contain v contains sharp, or x contains this symbol hash. This is because if v or x contain the hashes, then when you pump it more, then you will end up getting more number of hashes than what you had earlier. So that is clearly not in the language, because it only has two hash symbols and some number of zeros satisfying some constraint. But if your v or x contain sharp, then they will end up pumping more of the hashes, which is clearly out of the syntax. So this cannot happen, this is not possible. Okay, so that means yeah, so that means either, so case 1 is that either your chunk of vwx is entirely contained somewhere. So if these are the two markers, then maybe the vwx chunk already lies somewhere here. Okay, then what happens is, when we pump this, pump some vwx at least one more time, then you will end up now increasing the number of zeros here, but the number of zeros on this side is fixed. So we already had n zeros here, we had 3n zeros here, and 2n many here. So these two we are not touching, these two remain the same, but here we are increasing the number of zeros. So this is clearly not a string in the language, because if there are n zeros and 3n zeros at the front and back respectively, then the middle chunk should respect it by only keeping 2n zeros, so which is not happening here. So it cannot be that vwx is a string that is entirely contained within either one of the three chunks. The case 2 is that maybe it is interspersed. So maybe there is a part of w here, there's a part of w here, and maybe v is some number of zeros here, and x is maybe some number of zeros here, vwx. So this is, let's say this is the condition. Okay, so in either case what will happen is, when we pump, either we increase the number of zeros to the left or we increase the number of zeros to the right, but the number of zeros here is fixed, which is 3n. So then either we are increasing this number by more than 2n, or we are increasing this number by more than n, or we are doing both. So again there is a contradiction, because it is not going to give us a string of the form 0 to the n separated with 2n zeros separated with 3n zeros. So these are the only three cases that are possible, and again in each of the cases we argued that we get a contradiction on pumping. Okay, so again this is that so this language is also not context free. So now we will look at the third example, and this is this is slightly different from the first two, and it will require somewhat somewhat of a new trick to work. So okay, I'll get this on a new page. Okay, so the part C is set of all w sharp t such that t is a substring, sorry, w is a substring of t. Okay, so in this example, one thing is that in the previous one you already had the string given to you, and the only job was to do some kind of a separation and show that in any case there is a contradiction. But here w and t are not even given to us, so we have to make a useful choice of w and t such that it will help us in doing the analysis. So this is one challenge with the problem, that first is we have to identify what is w and t, and secondly, as you try to solve, you will see that you hit a block, in the sense that no matter what w and t you choose, if you try to pump it up, it will not give a contradiction. So we have to do something more. So maybe if you would like to try for 2 minutes, I'll wait. Okay, so let's discuss this. So suppose okay, suppose w is suppose the string that we are looking at is 0 to the n 1 to the n separated with 0 to the n 1 to the n. So this is a valid string in the given language, because any string is a substring of itself. So in this case w and t are equal, but w is still a substring of t, so it is still in the language. So this is the string that we have, and it is kind of similar. Now we have an example that is kind of similar to what we saw in the first example. So here we had 0 to the n 1 to the n followed by 0 to the n 1 to the n. It's a similar example that we are looking at, but we have a separator sharp here, which is only going to help us. So this is in the language because 0 to the n 1 to the n is a substring of 0 to the n 1 to the n. So this is what you have. And yeah, and what we're now going to do is we are going to show that no matter how you break this, so u v w x y, no matter how you break this, you are only going to you are only going to get a string in the language, and we'll show a contradiction for this. So like we said earlier, notice that v or x cannot contain the symbol hash, because if it does, then it will end up pumping more hashes, then you would end up getting more hash than what you already had, which is outside the syntax. So this is clearly not the case. So then what we can assume is either so then what we can assume is that this is some zeros followed by some ones followed by separator, and zeros followed by ones. So what is possible is maybe this vxy is contained entirely in one block. So maybe this is vxy. Now if you pump it up, then what will happen is you will get a string 0 to the n 1 to the m separated with 0 to the n 1 to the n 1 to the n, where m is strictly greater than n, because we are pumping up. So for I greater than equal to 2, you will have that u v to the I w x to the vwx, x to the iy. So this will be of this form where m is strictly greater than n, and we know that this is not in the language. So this is not in the language, so this can't happen. Similarly, if instead of number of ones, if let's say it is contained entirely within number of zeros, then you get a similar contradiction. In this case, you get 0 to the n 1 to the n separated with 0 to the n 1 to the n, where m is greater than n. Then again you get a similar contradiction. So all these cases are similar. The only case that we haven't considered is when these are like interspersed somewhere here. So let's look at that case. Suppose you have set of zeros, set of ones separated with set of zeros, set of ones, and let's say that your vwx lies somewhere here. Okay, so now what happens is if you pump up the string, then either you will end up increasing the number of zeros or you will end up increasing the number of ones. Then this string here is clearly of length larger than the length of the string here. So if this is maybe length p1 and this is length p2, then p1 is clearly length more than p2. Then a string of larger length can never be a substring of a string of smaller length, because when you say substring, you are looking at a smaller part of, possibly smaller part of it. It can't happen that a substring is larger than the given string itself. So this is again a contradiction, because p1 is greater than p2, so the first string cannot be a substring of the second string. So this cannot happen. But what about the other case? So the other case would be that maybe vwx does not lie on the left part, maybe it lies on the right part. In this case, if you end up blowing up this chunk, there is still no contradiction. So that means, suppose you have a set of zeros here, then you have a set of ones, n many zeros followed by n many ones, then you have a separator and n zeros followed by n ones. This is the string, and let's say that vwx lies here. Now suppose you pump up the string, then what, maybe you get 0 to the n plus 1 followed by 1 to the n plus 1, and here you have 0 to the n 1 to the n, which was untouched. So notice that this string is still a substring of 0 to the n plus 1 1 to the n plus 1, because this is 0 followed by n zeros then you have n ones followed by 1 1. So this substring occurs here, this 0 to the n, 1 to the n occurs in the larger string. So in this case, no matter how you try to try to distribute this part here, if it is on the right hand side, it will end up giving you a substring only. So there is no easy way to get a contradiction if we pump up. But what we will do is, we will use the trick of pumping down. This is something we saw in the case of regular languages also. Whenever pumping up does not help us, the trick is to use pumping down. What do we mean by that? So that means u v w x y is going to be in the language for all I greater than equal to 0. So in particular, you choose I equal to 0. So that means you're cutting down on some zeros or you're cutting down on some ones, because instead of letting it occur once, we are removing that part. So either we are removing a part of zeros from here, or we are removing a part of ones from here. Suppose that, without loss of generality, let v be some number of k's or some number of zeros. Then what does u v to the 0 w x to the 0 y look like? This will be 0 to the n, 1 to the n sharp 0 to the n minus k followed by 1 to the n, let's say. So this, in this case, you strictly get the number of zeros which is lesser than what is the number of zeros here. Or if you do it for ones, then you end up getting that the number of ones on the right is lesser than the number of ones on the left. So in either case, we get a contradiction. Okay, so that was the whole trick. So what we did is, the first challenge was to identify the correct w and t. And once we got the w and t correctly, which was 0 to the n, 1 to the n followed by 0 to the n, 1 to the n, we looked at all the cases. First we said that v and x cannot contain hash. If it does, then the syntax is broken. Then we said that okay, maybe vwx is contained entirely in a chunk within the set of ones or within the set of zeros. Then you end up breaking the structure again, you get more number of ones or more number of zeros. Then we look at the second case. Second case was, maybe it is on the left hand side of the hash, but it is interspersed. In that case, you see that the string is strictly longer or strictly larger than the string to the right, so it cannot be a substring. So again, there is a contradiction. Then we look at the third case, when instead of instead of the string on the left, we are pumping on the string on the right. But if we try to pump it up, we don't get a contradiction, because no matter how many times you pump, you will still end up getting the substring. So in order to get a contradiction, we use a trick which is called pumping down. And by pumping down, we mean that in this u v to the I, w x to the I y, we choose I to be 0. And once you choose I to the 0, we are going to either cut down on number of zeros or on number of ones. Then in that case, you get that the string on the right is strictly smaller than the string on the left. So again, you get a contradiction. Therefore, it can't be a substring, and that gives you the contradiction. So hence, no matter how you break it up, you end up with in a contradiction. So are there any questions about this example or any of the things that we have seen so far? Okay, one second. Okay, so if that is clear, let's look at the next example. Okay, so so this is something that we saw last time, but I wanted to discuss this in detail. So if there is time today towards the end of the tutorial, then we will discuss this. So so what we will do is, we will do some examples on Turing machines, and then if there is time, we will come back to this question. So let us recall what is the Turing machine model. Okay, so what is a Turing machine? Okay, so we saw several models so far. We know that there are DFAs more powerful. We have PDAs. Now we will define what is called a Turing machine. So in a Turing machine is a model which is even more powerful than what a push down automaton is. So this is defined by a 7 tuple. So you have a set of states. So you have a set of states, you have input alphabet, then you have stack alphabet, the tape alphabet, then you have a start state, you have two special states, one for accept, one for reject, and you have a transition function. So this is not maybe the same order in which you might have seen in the course, but yeah, just for the sake of tutorial. So this is the set of states, this is the input alphabet, then you have the tape alphabet, this is your start state, this is the accept state, and this is the reject state, and this is the transition function. Okay, so the transition function is a function from the set of states cross input alphabet. It tells you which state to go to, it tells you what to write, sorry, it tells you what to write on the tape, and it tells you whether to move to the left or to the right. So what do we mean by that? So there is, the Turing machine model looks like this. So there is something called an input tape, and initially all the input is written here, so it's some 0101 something like that, and this is read only. Okay, then you have what is called a work tape. This is the work tip. This is where you can write write and do calculations and so on. So this tape is infinite on the right hand side. There are other models also, but what we will do is we'll stick to this model where this end is infinite, so it is infinitely long. You can write here, you can rewrite here, and something like that. And blank is a special symbol which tells you that there is nothing written on it. So this is what the work tape looks like. This you can write, read or write. This is allowed. Then, like in case of DFS, you have what is called a head. So this is a head pointer which tells you where, what cell of the tape you are reading. So if it is pointing here, that means this is what you are going to read next, and here it's going to tell you what state you are in. So uh, yeah, so the rest of the things are very similar to the other models, except that here you make a decision to move to the left or move to the right. So if it says that you move to the right, then this pointer will move here to the next cell. If it says move to the left, it will move one step to the left. So um, yeah, so that is basically roughly the Turing machine model, and I mean, I think it will get clear once we start looking at the example. But one more thing that is worth noting is that what all the transitions are going to tell you that if you are at some state, let's say you are at q0, and let's say that you are reading the symbol, let's say this particular cell, then it tells you what state you should go in, what you should write. Maybe you just write 0 or you write 1, whatever it tells you. But it also tells you whether to go to the left or whether to go to the right. So let's say it tells you to go to left. Okay, so one thing is that no matter what you read, it is going to tell you where to go. Either you go to the left or you go to the right. Then when do we stop? When do we decide whether to accept or whether to reject? In case of DFAs and PDAs, it was simple because we had an acceptance condition. For DFAs, it was that if you are done reading the input, at the end, if you reach at the final state, then accept. If you don't reach at a final state, then reject. For PDAs, it was that if you have exhausted the stack, if the stack is empty, and you have finished reading the string, and you landed up in the final state, then accept, otherwise you reject. But in this case, there is no such notion of empty stack or finishing input, because it just keeps reading infinitely. So in order to stop that from happening, we have two special states. So one is called T, this is the accept state, and one is called R, this is the reject state. So what this does is that if in the throughout the computation, if you ever reach accept state, then it tells you you're going to stick there. From this point, we will never go to a non-final state. So from here, no matter what you see, we just stay. So then you say that it accepted. Similarly, if it ever reaches the reject state for the first time, then the entire string will be rejected. You just stay, no matter what you see, we are going to stay in the reject state. So that is how we define the notion of accept and reject state. So yeah, so with that in mind, here is a simple starting sort of like a warm-up example for Turing machines. So the question is, we know that uh, it is possible to design DFAs which accepts only those strings that have even number of ones. So the question is, if you want to design Turing machine for the same, then how many minimum states it will take? So yeah, so maybe you can try this for some time. We will discuss the solution. Sorry. If you have any solutions, please you could use the chat. Yeah, that would help. Okay, so yeah, so let's see the solution. So we know that for DFAs, you can have two state DFA for the same. So what does it look like? You have a Q0. If you see a 1, you go to Q1. If you see a 1 further, you go to Q0. And this state captures odd number of ones, and here it captures even number of ones. So if you want to accept even ones, then this is the DFA for it. But now for Turing machines, there is um, yeah, if we modify this, let's say attempt 1, I'll call this attempt 1. So this is a DFA. So if we modify this, let's say as follows. So Q0 is the start state of the Turing machine. If it sees zeros, uh, then let's say it writes 0 and goes to the right. Then if it sees 1, it writes 1 on that tape and goes to the right, and similarly does the same thing. 0 goes to the right, 1 goes to the right. Okay, so if this is what it does and we want to accept here, then there is a problem, because it will end up accepting strings like uh, 0 1 1 0 1 1 1 and so on. So this string, let's say, suppose this is x, then the number of ones here is odd. So this string should be rejected. But if this is the Turing machine, if this is the Turing machine that we have designed, then it will still accept it, because um, the problem is that this is our accept state, which is nothing but t. And what we said is that by design the accept state is such that if you ever reach that state t, then it will stay in accept state, it will never go, it will never move out of that state. So this is how we defined our special accept state. Sorry. Yeah, so this is how we define the special accept and special reject state. It says if you touch it, you will never move out of it. So that's why it can't be that this state is a final state for us and this state is a reject state for us. We need to have extra special state. So the problem with this is that this does not respect the definition of t and r. So what we need to do is, you start with q0. If you see zeros, you write 0, go to the right. If you see 1, you write 1 and go to the right. Same thing you do for this and here. But now what we do is, let's say we are done reading the string. So we went on reading the string, kept on moving to the right. Let's say we are done reading the string, then there will be set of blank symbols which tell you there is nothing written on that. So the moment you see a blank symbol, we know that we are done reading the string. And if you are in q0, then we know that the number of ones that we have seen is even. So that means we should accept. So from t, if no matter what you see, we are just going to stay here. So yeah, doesn't matter, you just stay here. And if you see a 1, you should still stay here. Similarly, if we are done reading the input for the input, and we are still in state q1, that means the number of ones were odd. So we go to this special state which is reject, and from here, no matter what we see, we are just going to reject. So because of this condition that the special, there are special states called accept and reject in the Turing machine, which if you hit once, you are going to stay there. So because of that extra condition, our Turing machine needs 2 more states in this case. So that's why a Turing machine must have 4 states. So is this okay, or are there any questions about this? If there are, please ask. So yeah, the answer is D, which is okay. So I hope that is clear. Now what we will do is, we will design one Turing machine for the given language. So let's say L is the set of all strings which have number of zeros which is a power of 2. So the number of, so L is like, it could have 1 0, 2 zeros, 4 zeros, 8 zeros, then 16 zeros, and so on. So basically it's the number of zeros where the string of zeros where number of zeros is a power of 2. So this is what the language is. Now the question is, design a Turing machine for the language L. So yeah, so by that we mean either you could draw the diagram which we, similar to what we drew in the previous example, or you can give the transitions for every state, and basically you can describe the 7 tuple. So I mean, just so that I'll wait for some 2 minutes so that you can try if you would like to, then we will discuss the solution. Okay, so let's see the solution. um, yeah, so let us write the informal idea first. So informal idea is that this is something that we discussed in the previous tutorial also. If you want to see whether the number of zeros, or I mean if a number is a power of 2, then the simple trick is that if yeah, so yeah, you are right. So the simple yeah, the idea is that if a number is a power of 2, if n is a power of 2, then if you divide it uh, any number of times, it will still be a power of 2. Then n by 2 is a power of 2. So for example, if you look at 8, if you divide it by 2, then you get to 4. If you divide it by 2, you get to 1. You get to 2, divide by 2, and you get to 1. So this happens for every power of 2. But for example, it is not enough to stop somewhere in between. So we can't do divide by 2. If the number is even, then accept. Because let's say the number was 6, or let's say the number was 12. If you divide by 2, then you get 6. But we should not accept simply at this point because 6 is even. Because if you divide this further, then you get 3, which is not a power of 2. In fact, 12 itself is not a power of 2. The next power of 8 is 16. So it is not enough. The idea is right that you divide by 2 and you get even number, but the point is we have to keep on doing this until we finally reach 1, so that we can conclude the number is actually a power of 2. If we stop in the middle, then it may not be a power of 2. Like for example, here it was for the case of 12. So yeah, so that is the informal idea. We will write this here. So idea is that first you um, yeah um, you have this tape where you have some zeros written. So what we will do is, for the first 0 that we read, we are going to keep it 0 only, but for the next 0 that we read, we will cross it off. We will remove it by writing, let's say, x. Then you see the third 0, we write 0 as it is, but the fourth 0 we will cross it off. Fifth one we will keep, and so on. So if there were 16 zeros here, then in the first step we would have reduced the number of zeros to half, which is 8. So that is the whole idea. But once we are done reading this, our head is going to be pointing to the right. So from that point, what we'll do is we will skip all the way back and come to the front, bring this head to the front, and repeat the same thing. So then next time we divide it by 2, divided by 2. Finally, if the number of ones is one, number of zeros is 1, then accept. So the idea is scan sweep all the way to the right by crossing off every alternate zeros. If number of zeros is odd, then reject already odd and not equal to 1 or more than 1, then already reject. Otherwise we keep all the way back. So sweep all the way to the right and repeat. And if the number of zeros is equal to 1, we've already reached the number. So like we said earlier, 8 goes to 4, 4 goes to 2, 2 goes to 1. The moment you get to 1, we are going to accept. So if the number of zeros is 1, then we will accept. So this is the informal idea. So first we are having it, we are going all the way back to the front. halving it again, going all the way back to the front. If number of ones is 1, then we going number of zeros is 1, then we accept. So how do we write this in terms of the state diagram? Suppose you are at q0 and you see some 0. So what we will do is we will write it as it is, go to the new state. Then then if you see another 0, then we want to cross it off. So if you see one more 0, we are going to cross the second 0 off. And yeah and the third time if you see a 0, then we want to keep it, so you go to q3. But if you see sorry, there's no need to make a new state, you just go back here. So if you see more 0, then you just so this loop is going to take care of the fact that the second 0 is crossed off and the first 0 is kept. So this is crossed and kept, and this loop keeps on happening. But it is also possible that while skimming, it is possible that there are some crosses that we have made that you come across. So we just want to ignore the crosses. So this is for ignoring crosses. If you see an x, write an x and keep moving to the right. If you see x, write an x and keep moving to the right. So it's just to ignore the excess, the markers that we had removed. Now the question is, now the point is that we have reached all the way to the right, so we want to come back to the left. So what we do is, let's say we are here and we have finished reading. So this is that means you have reached the blank symbol. So if you are at q2, that means um, yeah that means we have already crossed read 1 0 and one more 0. So we have seen even number of zeros. So q2 is a uh, is a good indication for us, which means that we should continue the process. So if you see this, then q3 will basically go all the way to the left. So what q3 does is, you have seen some input here, you came all the way here, then it takes you back to where you started without changing the input. So q3 basically, no matter what you see, it is just going to take you to the left. Then from there, if you see the left hand marker, then you should turn to the right. So you go all the way to the left. If you see the left hand marker, that means you have reached the left end of the input, so you should start scanning to the right. So hence this transition will take you back to where you started. But if you are at q1 and you see a blank symbol, okay, so if we are at q1 and we see a blank symbol, what that means is that we have seen odd number of zeros, because q1 just says you saw a 0, you replaced it with a 0, and there is nothing, no more zeros that are remaining. So that means the number of uh, the number of zeros that we have seen here is odd. So we should we should be rejecting at this point. Okay, so and no matter what you see, we are just going to we are just going to reject it. Okay, so okay, one thing I haven't taken care of here is the accept state. So we want to make an accept state such that you've only seen such that you have only seen one occurrence of 0, and that is when you should be accepting. Okay, okay, so I think one small modification that we can make to this is, um, is possibly that you, instead of looking for one occurrence of 0, you look for, I mean, instead of um, okay. So I don't know. I don't know if instead of keeping the first zero and crossing of the second zero, if we do the reverse thing, that is cross of the first zero and keep the second zero, is it uh, is it easy to modify this? Okay, so just give me a minute. Okay, yeah, okay. I think we can do a small modification here. So okay, so what we'll do is okay, so what we do is we come back to this state, call this q4 if we have reached uh, the extreme left of it. Then if you see one occurrence of 0, um, let's say you see one occurrence of 0, you go to the left. Let's say you go to state q5. From this point, yeah, then if you see any number of x's, we are just going to ignore and keep moving to the left. Then if you see one more occurrence of 0, then that means that there were odd number of zeros and there were more than one odd number of zeros. So this is the condition that we said. If number of zeros is odd, then we want to reject, but if number of zeros is 1, then we want to accept. So any odd number of zeros which is more than 1 is what we want to reject. So in this case, if we reach at q1, we know it is odd. So there are two things we want to check. Is it equal to 1? Is the number of zeros equal to 1, or is it more than 1? So this is the first occurrence of 0 on q5. If from this point you see more zeros, then that means you should reject. So this is the reject state. No matter what you see, we should reject this. Okay, and if we never reach to q5, to this state, that is there is no occurrence of no more zeros, then um, yeah, then you will reach the left hand marker, and from that point we should accept. So this is the special accept state. Okay, so basically what we did is, here we know that number of occurrences is odd, but is it equal to 1 or is it more than 1? If it is more than 1, then it will go to the reject state. If it is equal to 1, then from q5 it will directly go to the accept state. So yeah, so that is the only modification we did, but I think it would be easier to make the same, to draw automaton for the same, if we cross off the first one and keep the second one. So in that case we don't have to make this condition check. Okay, so in that case we don't have to make this condition check of I mean this thing, uh, q4 q5 thing. Maybe it may be simpler, but I hope this idea is clear. Or if there are any questions, then let me know. So there's some message in the chat, but I did not understand. So first n even zeros accept. Okay, so I have just one more question that is somewhat easier. I hope this example was clear. So it's just that we are having the zeros and checking the conditions again and again. So we will define what is called, this is called instantaneous description. So of a Turing machine. So one thing we know is that if we look at in case of PDAs also, we define what is called instantaneous description. That means if at any point of execution, if you take a snapshot of the machine, what does it look like? So that's basically the idea. So this is also called configurations. This goes by the name configuration, but in the lectures this was referred to as instantaneous description, so I will stick to it. So this is your tape, this is the left hand marker, and you have some content written here, and the tape is infinite on the right side. Then there is a head which is pointing at some cell, and you are in certain state. So let's say this is cell 1, cell 2, cell 3, cell 4, and so on. So if I say so the machine keeps moving left and right based on based on the transition that is given. So you are at this state, you are at the particular cell 4, and if you see a 0, then the machine tells you whether you should go to the right, whether you should go to the left, which state to go in, and what to write, all that. So this is a continuously moving machine. But if you say if you stop it at some point, if you pause the execution, then what does it look like? So this is exactly what it would look like if you take a snapshot. So what all information it has? It has a state q, which state you are in currently. It tells you which state you which cell you are in. So I is the cell number, so it could be a number, any natural number. In this case it is 4. And tells you what is the content on the string. So you can think of this as a string. So this is gamma star. So in the particular example we have taken, the snapshot is q0 because you are in state q0, and the cell number is 4, and the content looks like there is a left header, left marker, then you have 0 1 0 0, and let's say everything else is 0. You have several number of zeros, then you have blank symbols. So this is the snapshot. This is what is called the instantaneous description of the Turing machine. So what this question says is that in the previous example we drew one Turing machine, and let's say you are executing these strings 0 0 0, and this is 6 number of zeros. So question is, if you are uh, done reading these many strings, then what does the snapshot look like? So let me get the Turing machine here. Okay, so let's say this is the machine that we have, and we are reading the string 0. So what does it look like? So you have um, sorry, yeah, so you have this string 0 which is written, and okay, so maybe I'll wait for 1 minute. If you want to try, then we will discuss. So I'll show you the question also. Yeah. Okay, so let's see the solution for part A. Oh, sorry. Sorry, 1 second. Yeah. Okay. So let's say, yeah, let's say this is the tape that we have, and the for the first example, the string that is written is 0, and there is blank symbols. That's it. So initially the configuration of the any Turing machine starts like this. It is always pointing at this at the left hand marker. So the configuration will be left hand marker, sorry, q0, and the cell number is 0 because it always starts with the 0th cell. And what is the string? The string is uh, left hand marker followed by 0 followed by blank symbol. There are lots of blank symbol, infinitely many, but we won't be writing that. So this is the first configuration. Then what does it do? uh, we look at we are at q0 and the string that we read is 0. It tells you to write a 0. And okay, so how do we go to q5? Okay, in this case, the okay, so yeah, you're right. So it will eventually be, sorry, yeah, it will eventually go follow this path and go to the accept state t. That is right. But uh, yeah, so we will do this step by step. So from q0, if you see a 0, then it says that you should go to the right. So it goes to the right, which is here. So it is on the first cell, and the state that we are in is q1 because this is the transition we are looking at. So it goes to the state q1. So the next configuration is you are in q1, the cell you are reading is 1, and the content on the tape is still the same because we did not change it. Then if you are at q1 and you see 0, sorry, um, okay, sorry, I think I moved one step further. So when we were at, sorry, yeah, when we were at q0, I sort of already assumed that we are reading 0. So that means I kind of started here. Okay, so okay, sorry about the confusion. Okay, so the point is that when we are at q0, we already started reading the 0, so I did not take the left hand marker into account. So for now I will skip that. So you are at q0 and you are in the first cell. If you see, okay, then what you do is you go to the right. So that means you are at cell 2 and you go to q1 and you see a blank symbol. So the configuration would be you go to q1, you are in cell 2 and you haven't changed anything. um yeah, sorry, this is q1, this would be q2. Yeah, if you are in q1 and you see a blank symbol, then you should go to q4. So this is q4 and the cell that you are reading is, sorry, the cell that you are reading is 2, and what we did is we did not change anything, so the content remains the same. Okay, then yeah, then what you do is you are at q4 and if you see 0, which is yeah, we are moving backwards now. So if we saw the first one and this is where we were, now we are starting to move backward. So when we move backward, you see one more 0. Okay, so let's say, this is q4 and we are at 1. Yeah, now it says that if you are at q4 and you see a 0, then you go to q5, then you move to the left, so you are in cell 0. And yeah, and the content on the tape does not change. Then from q5 you say that if you see the left hand marker, which is because we moved to the left, then you go to t. And um, yeah, then it doesn't matter what cell you are in, you are just going to stay there. So this is the set of configurations. I think, yeah, your answer in the chat, that is yeah, I think it is quite there, just that we have written each and every set of configurations, and once it reaches to T, it is going to stay in T. So okay, because there was some confusion in the beginning, so let me just clarify so that so what happened is that we started at q0 without looking at the left hand marker, whereas in this example, so that's why your initial configuration was you were at 0 looking at cell 1, and this was the content. So this was your start configuration. Okay, so this is where we were, and then we said that look at the first transition on 0, it goes to q1 and writes the same symbol but moves to the right. So it moved to the right, went to q1, so that's why we have q1 on cell 2, and the string is same. Then q2 says that if you see a blank symbol, then keep moving, move to the left, so that's why we had q4, and from 2 if you move to the left, then you see a 1. So yeah, so that's why we have a 1 here, and uh, then the rest of it is just the uh, same series of transitions. So yeah, and once you reach the final state, you kind of stay there. So for the rest of the examples, the number of the sequence of configurations is going to be slightly more than what we did in this example. So I won't be doing that, but yeah, I think it's a good exercise to try. So yeah, I think we're almost near 8 o'clock. So that's all I wanted to talk about for today. If there are any questions about whatever we discussed today, please let me know. Also, this was the final problem solving session, but there will be an additional session on Monday, the coming Monday, 15th April. Sorry, which is Monday, from 6 p.m. to 8 p.m. So this will be a summary session where we will talk about all the ideas that we have seen throughout the course. So yeah, so please do join. And if there are any questions about what we discussed today, then yeah, please ask. Otherwise, yeah, feel free to leave. Okay, I'll stop the recording.